Hello, you're listening to the Science of Everything podcast, episode 77, Nuclear Physics and Radioactivity. I'm your host, James Fodor. So in this episode, we're going to look at nuclear physics and radioactivity, obviously. Particularly, I want to talk a little bit about the physics of the nucleus and how the operations of the physics of the nucleus of an atom leads to the phenomenon of radioactivity. I also then want to talk about some of the applications of radioactivity in medicine, nuclear energy, a little bit about nuclear weapons, and some of the biological effects of radiation, as well as some misconceptions about radioactivity. Recommended pre-listing for this episode is episode 8, History of the Atom, which will just give you a little bit of background, which will help, although this episode will be mostly standalone, I hope. So, that being said, let's make a start. So first, I want to start by talking about the nucleus, which is sort of the crucial aspect of the atom that we need to understand in order to understand radioactivity. So, an atom consists of the nucleus, which is surrounded by electrons. Electrons don't contribute to radioactivity, well, at least for the most part. What we're going to talk about, we're going to focus on the nucleus. The nucleus of an atom consists of protons, which are positively charged, and neutrons, which do not have an electric charge. Positive electric charge of the protons in the nucleus balances out the negative charge of the electrons surrounding the nucleus, so therefore making an atom overall neutral. Of course, atoms can become charged to become ions, but again, that's not a nuclear effect, so that's not our concern for this episode. Chemistry is essentially the study of interactions between the electrons in different atoms and molecules. Pretty much everything that you study in chemistry, and most of biology as well, or biochemistry, the connection between the two, comes about because of interactions of electrons, movements of electrons. Nuclear physics is different in that it studies the interactions and behavior of the protons and neutrons in the nucleus. So it's a different focus of what we're looking at. Nuclear physics studies the nucleus, chemistry studies the electrons. So the nucleus, as I mentioned, is much smaller than the electron clouds that surround it. It's very, very small indeed, much smaller than the atom as a whole. All of those protons and neutrons are clumped together in a very small ball of the nucleus. The number of protons in an atom is the same as the atomic number of the atom, so hydrogen has the fewest protons, with only one proton for each atom. Something like uranium has, I think, 92 protons in each atom, plus a bunch more neutrons. Many elements will have about the same number of neutrons as protons, give or take. What we want to focus on in this episode is the physics of the nucleus, particularly radioactivity. Indeed, historically, it's sort of interesting because normally when you're teaching this, or if you read this about this in a textbook and so on, it will introduce the nucleus and its structure, protons and neutrons and all that, and then it will start to talk about radioactivity. But in fact, as is so often in the history of science, the discovery was the other way around. Radioactivity was discovered, or it was in the process of being discovered. They didn't understand exactly what it was at first. And in the process of studying the behavior of radioactive substances, they came to develop an understanding of the nucleus. In particular, the nucleus had internal structure consisting of particles that were emitted as radiation in certain types of radioactivity, protons and neutrons. So radiation was initially discovered, late 19th century I believe this was, following the observation that uranium salts could expose photographic plates, which was very surprising when it was first discovered. You know, photographic plates are essentially chemical plates, and so they're normally exposed by exposure to light or chemical development. But when they were, I think, accidentally placed next to samples of uranium salt would just be uranium bonded to another element, basically. But placing them next to each other leads to the photographic plates can lead to them being developed, and people wondered how this was. At first it was thought that it was due to the emission of X-rays by the salts in response to sunlight shining on the salts, thereby leading to emission of X-rays, thereby exposing the photographic plates. Obviously, because X-rays can expose photographic plates, that's how X-rays were originally discovered. However, later it was discovered that even when uranium was not demonstrably emitting X-rays, it could still expose the plates. Indeed, the strength of the radiation that was causing the exposure was shown to be independent of basically anything, alloys, temperature, sunlight, magnetic fields, or pretty much anything that was done, the only thing that mattered was the amount of uranium that was present. And this was taken to be, indeed, as is the case, an indication that the effect was nuclear in origin, rather than an effect of the electrons. Because if it was an effect of the electrons, you'd expect magnetic fields, or possibly sunlight, temperature, and other things to make a difference. Since it didn't, that indicated that it was unaffected by all of those all of these factors that mostly have an effect on the electrons surrounding the nucleus. The amount of substance is the only thing that matters for radiation, generally, and the amount of substance obviously affects the number of nuclei that are present, and so therefore affecting the total amount of radiation that's emitted. So you've probably heard of Madame Curie, or Marie Curie, who did some early work on radioactivity. She discovered radium and polonium, two radioactive elements. She was able to find that by a series of tests, the different types of radiation that are emitted, which I'll discuss a little bit more later on, but the three main types are alpha, beta, and gamma radiation. Really just that means that those are the first three letters in the Greek alphabet. So it's basically, type A, type B, and type C. And only later was it discovered what the actual difference between those was by testing them in magnetic fields and so on. So just wanted to give you a bit of a flavor of the history of the discovery of radioactivity. As you probably also know, that they did not originally know that radiation was dangerous, and the samples were handled, in what we would consider today very careless and dangerous ways, although at the time it wasn't known to be dangerous, and it's very likely contributed to or caused the death of a number of researchers in that field, including Marie Curie herself. Okay, so let's talk a little bit more about how radioactivity happens. So what have we established so far? We've established that there is this phenomenon whereby certain types of elements, like uranium, polonium, radium, as well as other things, emit some type of radiation. Radiation is just basically particles and or waves. Light is a type of radiation. It's not visible light that's emitted by radioactive sources, but it's some type of radiation that carries energy. So it can expose photographic plates. If you've got enough of it, it actually feels warm to the touch. So it's some type of energy that's emitted by these substances. The emission of the energy does not seem to depend upon, pretty much anything like external light or magnetic fields, or the alloys that the substances might be in. The only thing it seems to matter is the amount of substance that you have. The more of the substance, the more radiation is emitted. So what's going on here? How could this be happening? What's the cause of this? Well, to answer that question, we need to step back a moment and sort of ask the question, which I can't remember if I've discussed on this podcast before. I may have, but if not, it might be an interesting thing to think about. Why do the protons clump together in the nucleus? Remember, protons are positively charged. Two positively charged particles will repel each other. They'll push away from each other. That's why the electrons in the outer shells surrounding the nucleus tend to essentially stay on different sides of the nucleus, if you want to think of it that way. They push apart from each other and sort of spread out around the nucleus because they repel each other because they're both negatively charged. Why don't protons do that? Why do the protons clump together in the center if they're all positively charged? How does that make sense? Well, if the only force operating was the electromagnetic force, it wouldn't make any sense. The protons would fly apart from each other and all atoms would be unstable. But the reason that they do stay together is because there is an additional force, not the electromagnetic force and not the gravitational force. That would be far too small to have any effect at these scales. But rather, it's called the strong nuclear force. The strong nuclear force is essentially an attractive force that operates on protons and neutrons. It actually operates on quarks, which make up protons and neutrons, but I don't want to complicate things too much. So for now, we'll just think about it as operating on protons and neutrons. I am simplifying a bit here because there are complications about different types of the ways in the nuclear force operates. But anyway, basically, the strong nuclear force operates to cause protons to be attracted to each other when they're relatively close. Although, when they get too close, the strong nuclear force actually becomes repulsive again. That's what stops all of the protons from just sitting on top of each other in exactly the same place. So it's kind of a weird force. It's not like gravity or electromagnetism, which operate under an inverse square law. The strong nuclear force is sort of very complicated in how it operates. So it operates so that it will keep protons together, but not too closely together, in a sense. And remember that the strong nuclear force is independent of charge, so it affects both protons and neutrons. It does not affect the electrons. The electrons are too far away and are not affected by this force. So this is different. Neutrons are not electrically charged, so they're unaffected by electromagnetic forces. However, the strong nuclear force does not act on electric charge, and so it affects neutrons and protons in a similar way, causing them to bunch together and clump together in the nucleus. So since all of these protons and neutrons, which are called nucleons because they're both in the nucleus, are being attracted together by the strong nuclear force, if you want to pull them apart, if you were to somehow try to disassemble the nucleus, you would need to put in energy. The amount of energy that you would have to put in order to rip apart the nucleus is called the binding energy. And generally what we're interested in is the binding energy per nucleon. So you take the total binding energy of the nucleus and divide it by the number of protons and neutrons. So this is the binding energy per nucleon. The greater the binding energy per nucleon, the more stable the nucleus is, because the more work you'd have to do, the more energy you'd have to put in order to rip it apart. Here's the key point. This is why I'm telling you about this, because this is why radioactivity exists. Different elements and different isotopes of different elements have different binding energies per nucleon. That is, different elements and isotopes are differentially stable. Some are more stable than others. Not talking about electrons, you're talking about the nucleus. The nucleus of different elements is differentially stable. Some more so, some less so, depending on how much binding energy there is. Radioactivity essentially is the process of less stable elements or isotopes converting into more stable isotopes by rearrangements of their nucleons. That's the basic idea. As a result of these rearrangements, which we'll talk about in a little bit, radiation is emitted, and this is what we see when we measure radiation. This is what causes those photographic plates to be exposed, for example, because of that radiation that came from the rearrangement of the protons and the neutrons in the nucleus, so that they could occupy a more stable form, thereby releasing energy. The nucleus of an atom is just like the electrons of an atom. Remember, the electrons of an atom can be raised up to higher energy levels, although they'll sort of tend to go down to lower energy levels, emitting energy, generally in the form of photons, as they do that. Well, it's similar in the nucleus. It is somewhat more complicated. It's not exactly the same, but it's conceptually similar that the nucleus can have different energy states as well. It will tend to want to go into a lower energy state. When it does so, it releases energy in the form of radiation. That's the basic idea of why radioactivity occurs. So, in fact, radioactivity is just a generic word to describe all of those methods in which one type of nuclei can transform into another. And there are different ways, three main ways that we'll talk about. But radioactivity is just that process of transforming one nuclei into another, and basically always it's a less stable nuclei into a more stable nuclei, releasing the resultant difference in energy in the form of radiation. So now let's talk about the three main types of radiation that I want to focus on, or the three main types of radioactive decay. If you recall, they're alpha, beta, and gamma decay. So I'll start by talking about alpha decay. Alpha decay occurs when a parent nucleus emits an alpha particle, which consists of two protons and two neutrons. So I should explain this phraseology of the parent and the daughter nucleus. So remember, radioactivity is the process of converting one nuclei to another. The original nucleus we call the parent nucleus, and the nucleus after the radiation has been emitted, after the decay has occurred, we say, is called the daughter nucleus. So parent decays into the daughter. And of course then the daughter can in turn decay into something else. And you can have long decay chains of one thing decaying into another thing, decaying into another thing, and so on and so on. But for our purpose, we're just going to focus here on a single parent and a single daughter nucleus. Now, always, the daughter nucleus will be more stable than that is, it will have more binding energy per nucleon than the parent, and the transition between them from parent to daughter occurs with the emission of radiation. That difference in energy is emitted in the form of radiation. There are three different types, main different types of radiation, or different types of decay that can bring about this transition, the alpha, beta, and gamma. So the alpha, which is the first one that I just started talking about, occurs when the parent nucleus emits an alpha particle. Well, what's an alpha particle? As I said, it consists of two protons and two neutrons. So it's actually just a helium nucleus. Helium is the second element on the periodic table. That means it has two protons. Generally, helium also has two neutrons, although that can vary. But the standard form is two neutrons. It also generally has two electrons. But if you imagine ripping out the two electrons, you just have the nucleus. That's just an alpha particle. An alpha particle is just a helium nucleus, essentially. It has a charge of +2. So you can detect it using magnetic fields. A parent nucleus will only emit an alpha particle if doing so is favorable. That is, if the daughter nucleus has a higher binding energy per nucleon than the parent nucleus. So that's why most substances aren't just sort of emitting alpha particles all the time. It doesn't generally happen spontaneously. In fact, there's a high energy barrier against it happening, because remember, the strong nuclear force is pulling on the protons and the neutrons, keeping them together. The electromagnetic force is pushing them apart. So there's a sort of a battle between those. Generally, the strong nuclear force being stronger wins out. But if you can imagine sort of grabbing two of the protons and two neutrons, so a helium nucleus or an alpha particle, grabbing on one of those and sort of pulling. At first, it will be very hard to pull them away from the rest of the nucleons because of the strong nuclear binding force keeping them in. But as you get them a little bit further away, the attractive force diminishes. It diminishes with distance. And if you can get them far enough away, the attractive force will diminish enough so that the repulsive force of the positive charge of the protons will take over, and that will actually do the rest of the work for you. So it will push away. So it's a little bit hard to sort of imagine what that's like. It's sort of like pulling on a rubber band. Except the rubber band starts off really, really tight, but once you pull it beyond a certain point, it gets really loose and actually acts like a spring. But you've got to put that initial energy in to pull the alpha particle away. Once it gets far enough away, it will move away spontaneously because of the electromagnetic repulsion. But you have to put that initial energy in. And that initial energy barrier, and actually the reason this can occur at all is because of quantum tunneling effects, but we won't get into that now. That initial energy barrier is generally what stops this from occurring all of the time spontaneously. And it will only occur, or with any significant probability will occur, when the daughter nucleus is more stable than the parent nucleus. So that's alpha decay. It spits out an alpha particle. Alpha decay, since the parent nucleus loses two protons and two neutrons, it changes, the atomic number changes. So the atomic number goes down by 2, and the atomic mass goes down by 4, because you've lost the 4 nucleons. So that's alpha decay. Next type of decay is called beta decay. There are actually different types of beta decay, but the main type that I wanted to focus on is beta minus decay, where a neutron decays into a proton, emitting an electron in the process. Now, this is different to alpha decay because it doesn't emit a big fat helium nucleus consisting of 2 protons and 2 neutrons. It actually only just emits an electron, which is much smaller. Also, it occurs by a neutron decaying into a proton. Now, neutrons and protons we sort of generally think of as being roughly the same size, and that's true. They're very similar in mass, both much more massive than an electron. However, if you actually look at the precise numbers, a neutron is slightly more massive than a proton. And so, loosely speaking, you can think of a neutron as kind of like a proton and electron packed together. The proton is positively charged, the electron is negatively charged, and so brought together they have a neutral charge. But if the neutron can spit away the electron, then, well, it's left with the proton, and also it reduces, its mass is a little bit lower. Now, I stress that this is not literally true. A neutron is not literally a proton combined with an electron, but I'm just saying that for the purpose of understanding beta decay, you can think of it like that. A neutron is heavier than a proton, and if it spits out an electron, it can turn itself into a proton. Also note that if you turn a neutron into a proton, the atomic number of that nucleus, of that element, has actually increased. It's gone up by 1, and so therefore it's a new element now. You've actually moved 1 up the periodic table. So while alpha decay moves the parent nucleus 2 places down on the periodic table by lowering the atomic number by 2, beta minus decay actually increases the atomic number, moving it up by 1 on the periodic table. So different effects. Also different types of radiation emitted. In alpha decay, the radiation consists of alpha particles, which are positively charged. In beta decay, the radiation consists of electrons, which are negatively charged. The next type of decay that I want to talk about, and the final one, gamma decay, is different again from alpha and beta decay because it doesn't actually involve any changes in nucleons or any particle emissions. So beta decay going from the parent to the daughter nucleus, there's no change in the number of protons, no change in the number of electrons, no protons emitted, no electrons emitted, no neutrons emitted, nothing. Okay, so you might be thinking, well, if there are no protons or electrons if there are no protons or neutrons or electrons changed for that matter, then what's happening? I mean, surely something's happening, otherwise there wouldn't be a decay product, right? There wouldn't be any radiation emitted. Well, yes, there must be something happening in order to emit the radiation. What happens in gamma decay is that essentially the nucleus changes from a higher energy state to a lower energy state, or a lower energy level. Now, this is vaguely analogous to how an electron can move from a higher energy level around orbiting the nucleus to a lower one. The electron's still there. We haven't gained or lost electrons. It's just it's moved energy states. It's sort of similar in the nucleus. You can change the state configuration basically of protons and neutrons so that they're still all there. It's just they're in a lower energy state. But of course, the energy difference between the higher and lower state has to go somewhere. Well, it's emitted in the form of radiation. What form does that radiation take? Well, gamma radiation. Remember, gamma radiation is just a photon. It's fundamentally the same thing as visible light. It's just much higher frequency, higher energy. The reason it's so high energy is because the energy differences between the high and low energy states in the nucleus are much bigger than those for electrons. Because when electrons change energy states, and they often emit ultraviolet or maybe UV or maybe visible light, much lower in energies than the gamma radiations emitted by the nucleus when it changes in energy levels. So no change in the atomic number or atomic mass in the case of gamma decay, but there is emission of very high energy photons. Okay, so those are the three main types of decay: alpha decay, beta decay, gamma decay. Respectively, they involve the emission of alpha particles, 2 protons and 2 neutrons, beta particles, which are just electrons, and gamma rays, or photons, high-energy photons. Now, I just want to talk a little bit about measurement of radioactivity before we get on to some of the effects of radiation and misconceptions and then applications. So, measuring radiation. There are lots of different units of measurement that are applied to radiation, and I have been confused by this for a long time because there's a nice table on one of the Wikipedia pages. There are at least like 8 or 10 different ones. Some of them are not used much anymore. I will just focus here on the 3 different units of radiation that are used in the SI system. That is the standard, essentially the metric system that's used in science internationally. You will hear others reported, but they're generally older units that are not recommended to be used anymore. So the first way of measuring radioactivity is just to basically ask the question, how many nuclear decays occur within a given period of time for a particular sample? So if I've got a bunch of, if I had a bunch of uranium here of a certain mass, how many nuclear decay events occur? How many parents decay into daughters in a given period of time? Usually a second. One decay event in 1 second is called 1 becquerel, after one of the early investigators into this field. So a becquerel is a unit that measures the amount of radioactivity purely in terms of the number of decay events. That tells you how much decay is happening, but it doesn't tell you anything about the amount of energy released. And often that's what we're interested in, how much energy is being released, not just how many events are happening. So in order to measure the amount of energy released by a substance, we use a measurement called the gray. 1 gray is equal to 1 joule per kilogram. Being emitted or absorbed. Generally, we talk about it being absorbed because we're interested in radiation doses to people or other things like that. Now, note that while a becquerel is measured in terms of decays per second, a gray is not a rate, so it's not per second. It's just an amount. So the becquerel reading of a radioactive substance won't depend on how much time you measure it for. It may change over time, but it doesn't build over time because it's a rate. It's the number of decays per second. Whereas gray is an amount of energy per kilogram. So that's useful because we're often interested in knowing how much radiation energy a person has been exposed to per kilogram of body tissue, for example. So, but the thing about a gray is that it increases over time with exposure. The third unit that I want to mention is called a sievert. Sieverts are also measured in joules per kilogram, but it's different to a gray because while a gray just measures the amount of energy absorbed or emitted, a sievert measures the biological impact of that energy. So you can measure grays just by, purely using physics, essentially. You calculate the amount of energy released in alpha particles or gamma rays or whatever, and then divide by the mass of whatever substance you're concerned about. Sieverts cannot be measured purely as a physical process because it depends on the biological effect of that radiation. So a sievert represents the equivalent biological effect of the deposit of a joule of radiation energy in a kilogram of human tissue determined by medical study. So there's an equivalent standard that depends upon particularly what type of radiation it is and where it is absorbed on the body. So that's determined through medical studies. So a sievert is quite different from a grey in that sense, even though that they kind of sound similar if you just look at the units. So sieverts is the most sort of relevant measurement of radiation exposure if what you're interested in is the biological effect of the radiation. If you're interested in the total amount of energy, greys is more useful. If you're interested in the number of decay events, you want to use becquerels. So let's now talk a little bit about some of the biological effects of radiation, radioactivity. Why are people worried about radiation? So generally the most common associations of radioactivity or radiation is that it's dangerous, harmful, scary. And it can be, because it can be dangerous. But it's important to understand that we are all exposed to radiation all of the time. I mean, for starters, whenever you see anything, you're detecting radiation. But even if we ignore that and just focus on gamma radiation and alpha and beta particles, the type that we've been mostly focusing on, even that we are exposed to all of the time from nature. There are all sorts of causes of radioactivity from nature, and exposure to radiation is, well, part of life. It's all about the level of exposure and the total amount of exposure, generally measured in sieverts in terms of its biological impact. But the question that I want to address really is, why is radiation dangerous? I mean, fundamentally, it's just, photons or electrons or alpha particles. What's dangerous about that? And why exactly do people die from radiation exposure or radiation poisoning you've probably heard of? What actually kills them? Well, the reason radiation is damaging for the most part is because it's ionizing. You've probably heard of ionizing radiation before. The concept of what ionizing means is very simple. It just means that it can remove electrons from an atom or a molecule, causing it to become an ion, become charged. Now, why is that a problem? It wouldn't be a problem if we were all just, say, rocks or simple substances. That's why radiation doesn't generally harm structures. Radiation itself doesn't, although very large amounts of energy can. Because losing a few electrons here and there is not really going to harm a substance like a rock that's fairly sort of simple. However, biological tissues are anything but simple. They consist of many different sorts of intricately complicated biochemicals, which for their function require very specific arrangements of atoms and electrons. If you disrupt that by removing electrons here and there and creating ions, which can often then go and disrupt other biological activities, that creates havoc. It can destroy organic molecules and disrupt the activity of cells, leading to cell death. And if you kill enough cells, you can have organ failure, leading to organismal death. So it's all about, of course, the amount of damage. A little bit of ionization damage is not really going to harm an organism. A bit more can harm it a bit, and a bit more can harm it a bit more, and so on. It's about the relative amount. But fundamentally, that's what sort of short-term acute radiation exposure does, is that it disrupts the activity of any type of living tissue, potentially causing death. There's another effect that radiation can have, which is to cause cancer, which you probably also know about. That's a longer-term effect. It doesn't happen straight away. The reason that ionizing radiation can cause cancer is because ionization in the DNA molecules can cause mutations, changes of the bases, or the base pairs that store information. Ionizing radiation promotes mutations. Mutations happen anyway, but ionizing radiation can dramatically increase the rate of mutations. And some types of mutations can lead to cancer, particularly those that disrupt the ability of a cell to control its replication. So that's essentially why radiation can cause cancer. And again, it all depends on the dose and where it's received and so on. We don't know a great deal about the biological effects of radiation in the long term because it's very difficult to study, especially because, you can't ever, usually you can't say that someone got cancer because of radiation exposure unless it's a very extreme case. You can only determine these things at a sort of a statistical level. You can compare different populations of people who have had different levels of radiation exposure and look at the relative rates of different types of cancers in those populations and look for elevations. But of course, when you're doing that, you have to make sure that all of the other factors, including diet and exercise and genetics and everything else, smoking and everything else that affects cancer rates, has been kept constant, which is very hard to do. So it's very difficult to tell exactly what the long-term effects of radiation exposure are. It certainly is clear, though, that radiation exposure can increase the risk of cancer, especially in, again, extreme cases when we have very high rates of exposure. So that's the real concern. There's the acute radiation sickness damage, and you really have to have quite a lot of radiation exposure to feel any effects of that. Then there's the longer-term ongoing risk of elevated rates of cancer. Now that can occur even if people never experience any acute effects of radiation sickness, and that's in some sense it's the more damaging type because, people like Madame Curie, right? They didn't generally feel sick. Or I think actually sometimes they did if they were handling enough of it. But often you can handle a lot of this material or be exposed to it, but not in enough amounts to ever feel sick or ill-affected by it. That's because you're not, it's not disrupting your cellular function enough for you to feel it. But it can be causing those long-term effects and increasing the rate of mutations, which in the long term can lead to increased risk of cancer. And that's why we generally want to protect ourselves from radiation, either by reducing the risk at source or by shielding. Different types of shielding are used depending upon the type of particle. It's, as I mentioned, quite easy to shield against alpha and beta particles. In fact, you don't even really need to shield against alpha particles because air is generally a pretty good shield against them, or just a single sheet of paper, even very energetic ones, because they're so big. Beta particles, a couple of millimeters of aluminium is generally enough to stop those. Gamma rays, as I mentioned, is the tricky one. You really need very dense substances and quite a lot of it to absorb gamma rays. Basically, the thicker you make it, the more you'll absorb, and you generally need something, a very dense substance. So lead is commonly used, but often many centimeters will be required in order to stop enough of the gamma rays. And of course, it just depends on, it's about the risk-benefit trade-off. The more shielding you install, the more expensive it is, and the more difficult it might be to run your machine or do whatever, but the safer you'll be. Of course, you can never stop 100% of the gamma rays, so it's all about that trade-off. Now that we've got some of the general theory about the nucleus and radioactivity, I want to talk briefly about some of the applications of radioactivity, some of its uses, and then close with some misconceptions about radioactivity, although some of those I've already touched on. First of all, I'll talk about radioactive dating, which you've probably heard of. For some reason, everyone's heard of carbon dating. Fewer people seem to have heard of uranium dating and potassium dating and these other forms. But there are many different... okay, so let me step back for a moment. There are some substances that are basically always radioactive. Mostly those are man-made substances like plutonium, which are not found in nature precisely because if and when they were ever created, they long since decayed away. But mostly radioactivity doesn't occur in those sort of substances, apart from in labs. Mostly radioactivity occurs in the form of isotopes. Remember, an isotope is the same number of protons but different number of neutrons for a given element. Isotopes of ordinary elements that are radioactive. So an example is carbon. Carbon's everywhere. We're made largely of carbon. Carbon-12 is the normal form of carbon. It's stable. It's not radioactive. It won't decay. Carbon-14 is an isotope with 2 extra neutrons. It is unstable. It will decay. Uranium is another example. Uranium, actually, I'm not sure if there are any stable isotopes of uranium. I'd have to look that up. But certainly there are different isotopes of uranium with differing half-lives. Uranium-238 has a much longer half-life than uranium-235. So it's much more unstable. Now, I mentioned this concept of half-life, and I realize I haven't explained that. So what is a half-life? Now remember, radioactivity is about parent nuclei decaying into daughter nuclei, because the daughter nuclei are more stable than the parent nuclei. They emit radiation in the process. Now that happens at some rate. It doesn't happen all at once. The rate at which it occurs depends essentially on the energy barrier between the two states. The lower the energy barrier, the more rapidly the decay will occur. Fundamentally, radioactivity is probabilistic. So if I have a given atom of uranium, say, I can never say when exactly it's going to decay. It might decay this second, it might not decay for 100 years. I really have no idea. However, it turns out that if I get lots and lots of uranium atoms and sort of record the time it takes them all to decay, there is very strong regularity as to how long on average it takes. And I can use this average figure to come up with what's called the half-life of a given isotope. Each isotope has its own half-life, and they can vary wildly from fractions of a second to many billions of years, depending on how rapidly this decay is going to occur. The half-life is defined as the amount of time that it would take for, on average, half of all of the parent parent atoms to decay into daughter atoms, or nuclei. So that's an average. It doesn't mean that exactly half of them are going to decay over that period of time, but it means on average. Of course, if you get enough of them, and generally, atoms are small, so it doesn't take much to get enough of them, billions, trillions, many trillions of atoms, you can say pretty much exactly if the material is going to decay after one half-life. That doesn't mean that after 2 half-lives, all of the material is decayed, because radioactivity is a memoryless process. The rate of radioactivity doesn't change over time, as far as we know. So a substance has no memory of sort of how long it's been decaying. It's not like it's sort of trying to decay and eventually will succeed. It's just given a bunch of atoms that are radioactive, half of them will decay in 1 half-life, and then whatever's left after the first half-life, half of that in turn will decay in 1 more half-life, and then in turn whatever's left after those 2 half-lives, which should be about 25% of the original, half of that again will decay after a further half-life, and so on and so on. As I mentioned, the half-lives can vary dramatically. Uranium-238 has a half-life of 4.5 billion years. Carbon-14 has a half-life of 5,700 years. So that's a very substantial difference. The fact that different isotopes have very different half-lives, and the fact that these half-lives are generally very stable, as far as we know, and there are various ways of testing this. Half-lives don't change over time. They're also generally unaffected by temperature or pressure or really any conditions that you could imagine. Again, for the most part, there are a few sort of random exceptions, but for the most part, they're unaffected by these things. As such, we can actually use the decay rates of these different substances as a way of dating materials that we would otherwise not know the age of. So by comparing the isotopic ratios of very old rocks, for example, ratios of uranium and lead and other things, we can make an estimate of how old they are. Carbon dating, as I mentioned before, and as many people have heard of, is a way not of dating rocks, but of dating organic materials or organic substances. When an organism is alive, the carbon atoms in that organism's body are constantly being exchanged with the environment through metabolism and breathing and stuff like that. And therefore, the ratio of carbon-14 to carbon-12 is kept constant relative to the atmospheric ratio. And the ratio in the atmosphere as a whole, in turn, is kept constant by a continual new supply of carbon-14 via cosmic rays, which are essentially high-energy particles coming from the sun, leading to production, leading to events which cause the production of carbon-14. We don't need to go into the details of that. So the carbon-14, carbon-12 ratio of the atmosphere is essentially constant over very long periods of time, or at least over the periods of time that we can that are relevant to carbon dating, which is tens of thousands of years. While it's alive, an organism also keeps its internal carbon ratio at the same ratio as the atmosphere as a whole due to that exchange of atoms I mentioned. However, once an organism dies, these atom exchanges stop, or mostly stop, because it's no longer breathing, it's no longer eating, it's no longer drinking, and so on. It's no longer exchanging material in this way with the environment. And the carbon-14 in its tissues begins to decay and change into carbon-12. So if you examine the carbon-12 to carbon-14 ratio of a plant or an animal, or really anything that has organic material in it, you can make an estimate as to how long ago it died. So this is very useful for dating not just animal and human remains, but also things like fabrics or wood or other things, again, that are derived from animal or plant products. Now, because carbon-14 has a half-life of 5,700 years, and every half-life means that 50% of the material has decayed, after, maybe 10 half-lives or so, there's very little carbon-14 left, and so we can't use carbon dating to go back further than maybe 50-ish thousand years. It's a bit of a fuzzy thing, but certainly we can't use carbon dating to date something like dinosaur material, because that's millions of years ago. So you can only use carbon dating for things that are relatively recent. Okay, so that's one application of radioactivity, radiocarbon dating, very useful technique. Another application is radiation therapy or radiotherapy, which essentially uses ionizing radiation to kill cancers or malignant cells, or at least keep them under control. Now, you might think, and many people find this odd when they learn about it, might think it's strange that radiation can cause cancer, but it's also used to treat cancer. What's the deal with that? Well, it's true. It's not necessarily a contradiction. Radiation can cause cancer by increasing the rate at which cells mutate, as I mentioned before. But it can also be used to kill cells. The actual difference here is the difference between the acute effects of radiation and the long-term effects of radiation. Because causing cancer is a long-term effect of radiation. It happens over long periods of time as a result of accumulation of mutations sped up by the ionizing radiation. The curative effect of radiation therapy is actually an acute effect. It's just if you blast cells with enough radiation, it will kill them, disrupt the metabolism so much by ionizing molecules that the cell will die. If you kill enough cancer cells, then you can effectively kill the tumor or eradicate it, or at least keep it under control. Now, the problem is that ionizing radiation doesn't distinguish between healthy cells and tumor cells. And so it will just sort of kill anything in its path. So if you just irradiated the whole person, well, you'd kill you'd take out the cancer, but you'd also kill the person. But anyway, in terms of radiation therapy, the way it's done is by, if you imagine radiation as a sort of a laser beam, it's not literally laser, but you can think of it like that. It's a narrow beam that's passed through part of the body and goes out the other side, or some of it will pass through the other side. And we're interested in just one sort of lump of tissue, which is the tumor. Now, you can imagine sort of grabbing that light and altering the angle so that we pass it through different angles. So it still hits the tumor, but it passes through different parts of the body on the way to and out from the tumor. So in that way, we ensure that other parts of the body that the radiation has to pass through sort of on the way to the tumor will get some radiation dosage. But because we're constantly changing the angle of the beam, they'll get only relatively small doses, whereas the constant bit, the part that gets that gets a dosage of radiation each time, is the tumor. So the tumor will get much more radiation dosage than the rest of the person, and hopefully therefore you'll be able to kill the tumor without exposing the rest of the patient to too much damage. Now, that's only useful if you have a relatively isolated tumor, or a few of them. If the tumors have metastasized throughout much of the body, then radiation therapy is not really going to work, because you just essentially you'd have to irradiate the entire person, in which case they'd be dead. So that's not really going to work. But it can be a useful therapy nonetheless to treat some forms of cancer. Final applications which I want to talk about, and these are probably the ones that people are most familiar with, essentially nuclear power and nuclear weapons. The principle of nuclear power is really quite simple. What you need to have is a radioactive substance that engages in a self-sustaining reaction. Self-sustaining meaning that, on average, one decay event triggers one other decay event. A decay event can trigger another decay event by releasing generally neutrons, which then interact with another atom, causing it in turn to decay. It's sort of like billiard balls hitting each other in a sense, except it's a bit more like you have a bunch of different clumps of billiard balls corresponding to each clump of billiard balls corresponding to, say, a uranium nucleus, and each billiard ball itself corresponding to a proton or a neutron. And when a neutron comes in, disrupting one of these clumps of balls, the balls sort of split up into two smaller groups, which are the decay products, and then a few lone neutrons are spit out as individual billiard balls, which then go and maybe hit another clump of billiard balls, causing it to split up. So this is a chain reaction, basically. One decay triggers further decays, and so on. Now, the rate at which this occurs is crucial. In order for nuclear power to work, you need the reaction to be self-sustaining, but not growing exponentially. So you pretty much need exactly the average number of decays caused by a decay to be 1. So one decay causes one other decay. If one decay causes more than one decay, the process will rapidly escalate, and you'll have essentially an explosion, a very rapid release of energy, which occurs when you get very rapid decay of a large portion of the substance all at once. You don't want that. On the other hand, if you have less than one decay caused by each decay event, then the reaction will gradually die out, and you don't want that either, because you want the reaction to keep going. So this is called the criticality, essentially, the number of reactions caused by each decay event. You want it to be essentially 1 in order for a sustained, controlled reaction. And this is essentially the trick with nuclear power, is to establish a system where you can very finely tune the rate at which the reaction is occurring. And this can be done by changing the what's called the enrichment of the fuel, which is essentially the isotopic ratio of uranium. Remember I mentioned there are different isotopes of uranium. Uranium-235 is much more radioactive than uranium-238. So more uranium-235 means a greater rate of reactivity, essentially. But you don't want it to be too high, so you want to get that ratio just right. There are also various other means that are used. There's the neutrons are generally slowed by a moderator, which can be all sorts of things. It can be water even, which helps which helps the neutrons slow down so that they can crash into the nuclei, thereby so they can crash into nuclei more readily, causing them to decay. It's actually, you might think faster neutrons would be more helpful, but actually it can be slower neutrons that can be better at triggering these chain reactions. So you want to control the amount of that you have and the number of neutrons you're absorbing. There are also things called control rods, which are made of neutron-absorbing material. Control rods are generally literally rods that you can sort of raise and lower into or out of the fuel. Lowering the control rods means that you're absorbing more neutrons, thereby each decay event triggers is less likely to trigger another decay event, so you're moving down away from criticality. On the other hand, if you raise them, then you're reducing the amount of neutrons you're absorbing, thereby increasing the amount of neutrons that are flying around, thereby increasing the average number of decay events that each decay event in turn causes, thereby you're moving towards criticality or beyond it, up above 1. So raising and lowering the control rods is another way of controlling the reaction. How does a nuclear reactor generate electricity, you might be wondering? How do you convert radiation, generally gamma rays, into electricity? Well, it's pretty much the same way that most energy sources generate electricity. It's basically by generating heat, which is used to create steam, which turns turbines. It's actually exactly the same way that coal power works. It's just that in coal power, the heat is generated by burning coal, which is a chemical reaction about moving electrons around, whereas in a nuclear power plant, the heat is generated by fissioning heavy elements, often uranium, into smaller elements, which releases energy, which then is used to turn the water into vapor. The big advantage of nuclear energy is that the amount of energy released per unit or per kilogram of fuel is much, much higher than for a chemical reaction. But I think it's something like 100,000 times. It's very, very substantially higher. So that is, to produce the amount of energy that you can produce with 1 kilogram of uranium, you would need many, 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 many kilograms of coal. That's the big advantage of nuclear power, is that it requires so much less fuel because it's much more energy efficient in that sense. So, I want to discuss nuclear weapons briefly because, we all want to know about those. But before I do, I just want to mention nuclear fusion. Nuclear fusion is the process that keeps the stars burning, or the sun shining. So fundamentally, almost all of the energy on Earth actually comes from, or did come from, fusion energy from the sun. Even coal power does, because burning coal derives from the energy originally stored by the plants, which when fossilized became coal, which in turn got it from photosynthesis by energy that was emitted from the sun. So even coal power is in some very indirect way fusion power. But anyway, fusion is essentially the opposite of fission. Nuclear fission, you take a big, heavy nucleus and split it up into smaller ones. It can be one smaller daughter nucleus, or you can actually have multiple daughter nuclei, or it can fragment into lots of pieces. But that's fission. It's breaking apart, and that releases energy. Nuclear fusion is the opposite. You put you will combine 2 or sometimes 3 small nuclei to form one bigger nuclei. That can also release energy. It just depends on what the nuclei are. Actually, it turns out that the most stable isotope is one of the isotopes of iron. I forget which version of iron. So it turns out that if you take elements less heavy than iron or more heavy than iron, either way you can produce energy. If you fuse elements less heavy than iron, that will release energy. Or if you fission elements more heavy than iron, that will also release energy. So iron's sort of that sweet spot where it's maximally stable. So this is why both fusion and fission can both release energy, which might seem counterintuitive. Given that they're opposites. It's not fusion and fission of exactly the same thing. You can't pull apart a uranium nucleus and release energy and then put it back together again and release more energy. That would be impossible. No, it's different elements. Generally, when you're fusing together, it's generally hydrogen that's fused together with helium. That's what the sun does. There are people who've been looking at ways of generating artificial fusion power. That's been under development for many decades. It's probably still got many more decades to go, but we're getting there. If we can crack fusion energy, that would be an enormous boon, because it would be extremely very cheap, produce an enormous amount of power. The fuel would be, I think, essentially seawater. You could any easy source of hydrogen really in order to fuel it, and you would not produce any radioactive wastes that nuclear plants do. So it would be a huge boon to civilization, but we're not there yet. Nuclear fusion is mostly used in nuclear weapons, where it's a way of essentially releasing even more energy than an ordinary fission bomb does. Let's then turn to talk a little bit about nuclear weapons. So, nuclear weapons are actually the first application of nuclear technology. They were developed by the United States during the Second World War and used for the first time at the very end of that conflict against Japan. It's the only time nuclear weapons have ever been used deliberately in combat, although there have been many tests and also accidents. The basic idea is simply that normal explosives operate by releasing chemical energy, again moving around those electrons. But we know that nuclear energy is much more dense in the sense that you need much less substance to produce the same amount of energy. So if you could release energy using a nuclear reaction, that would create a much bigger explosion, therefore causing more damage. That's the essential idea of a nuclear bomb. And that's essentially what it does. But nuclear bombs are difficult to make. In particular, you need a radioactive substance. But it's not just the radioactive substance. You need it to be sufficiently enriched, is the term that's used. Now, what that means is that ordinary uranium, say uranium-238, which is what most uranium is, it is radioactive, but it's not radioactive enough to generate an explosion. Now, remember when I talked about nuclear power, I talked about criticality, the idea that one decay event causes, on average, one other decay event, so that it's self-sustaining, but it doesn't escalate, it doesn't grow exponentially. That's what we want to generate power in a sustained way over time. But if we want an explosion, we want all of that energy coming out essentially as fast as we can. And we want it to be not self-sustaining, but growing exponentially with time. So we want it to reach supercritical state is the term. Now for that we need essentially enough radioactivity. We need enough of those decay events to happen. uranium-238 is not radioactive enough for that to happen. So you can't make a nuclear bomb with just uranium-238. You need the much more radioactive U-235. But uranium-235 is essentially not found by itself in nature precisely because it's so radioactive. It's found in small concentrations alongside uranium-238. So what has to be done in order to create weapons-grade uranium is to enrich uranium so that it has much more uranium-235 than it normally would in nature. I think in nature it's like 1% or something like that, or no, I think it's fractions of 1%. It's a very small amount. Weapons-grade uranium needs to have about 90% uranium-235 in order to be able to sustain the sort of exponentially accelerating process of one decay triggering more decays, which triggers more and more decays until essentially the whole substance decays in a very short period of time and releases a massive amount of energy, which then forms a big explosion. That's the goal of a nuclear bomb. You need highly radioactive substances to do that. Even the enriched uranium that's used in nuclear power plants isn't enough. That's usually only a few percent of uranium-235. That's not enough to sustain a nuclear explosion. So that's one reason why it's not possible for a nuclear power plant, even if absolutely everything goes wrong, it's not possible for it to go up in a nuclear explosion. The main danger about nuclear power plants is the enormous temperatures they generate. A nuclear power plant cannot go supercritical and explode like an atomic bomb can. Atomic bombs are difficult to make because you not only have to have that highly enriched uranium that I mentioned, but you also have to find a way of bringing it in to a sufficiently small space so that it's all clumped up together. Obviously, it has to be clumped up together because the whole idea is that one decay product then leads to more decay products. It's those billiard balls colliding each other, right? But for that to work, they have to be all close to each other. The more you spread it out, the harder it is for one reaction to trigger another reaction, and therefore the less likely you're going to have this chain reaction. So if I have lots of small quantities, even of highly enriched uranium, but if they're small amounts that are separated from each other, they're not really dangerous. They're only dangerous if I put them all together. You generally have to put them together and squeeze really tight. Not by holding your hands, obviously, but more like the way it's often done is by exploding the uranium into itself. Essentially, you can imagine like a sphere of explosion or a sphere of explosive material, just like ordinary TNT, ordinary chemical explosive material, that compress all of the enriched uranium together into a sort of really tight ball. Only then will you get the sufficient density of decay events in order to have this super accelerating process that allows you to get the supercritical massive release of energy that's required for a nuclear explosion. So it's actually very difficult to cause a nuclear explosion like this. You need the highly enriched fuel, and then even then you need to bring it together and compress it very tightly, very fast, in order to get the explosion to happen. If any of those things fails, you won't get a nuclear explosion. You may have heard of something called a thermonuclear weapon or a thermonuclear bomb. Or a fusion bomb, it's sometimes called, or a hydrogen bomb, it's also sometimes called. These are a more advanced and much deadlier form of nuclear weapon, which essentially uses... Okay, so remember how I said in order to trigger a nuclear detonation, you have to use first conventional explosive to essentially compress all of the nuclear material into a small enough space. Well, a similar process applies to if you want to have an explosion from release of fusion energy. Remember I said that you can fuse small elements together to release energy as well. And actually you can release more energy that way potentially. But it's harder to do because it requires even higher temperatures and pressures. So you can't get those just by having an ordinary detonation of TNT compressing them together. It's still not enough. But what if you used the TNT to compress together a bunch of, say, uranium, producing a nuclear explosion, and then use that in turn to compress together a bunch of light elements, which then would fuse, producing a thermonuclear explosion. So that's essentially the idea behind the hydrogen bomb, is that you use, there's an initial fission event, which then is able to trigger the sufficiently high temperatures and pressures needed in order to have a fusion explosion occurring, thereby releasing even more energy. So it's a multi-stage process to get the bigger bang, essentially. And in theory, you can sort of add as many of these in as you like, or at least many more. And people started to do this in the early 60s until they sort of realized that, that they were getting so dangerous that there was no way to test them because the blast radius and the radiation fallout would be too large. That it's not actually useful as a weapon because it will harm ourselves as well. Anyway, so that in theory you can make very, very large bombs that way. And it's not just the energy that they release, but it's also the radioactive material that they strew all over the place, and that's carried by wind currents, and that can settle over vast swaths of the world, which can lead to damaging, or not just damage to humans, but damage to wildlife. Crops won't grow. Yeah, very negative effects. Now, let's finish up with a few points about misconceptions about radioactivity, which I wanted to discuss, because there's a lot of misunderstanding across the public about how radioactivity works and what radioactivity is and sort of why it's dangerous or when it's dangerous and so on. So I've already mentioned that radioactivity is not man-made. There's often a conception that it's somehow artificial. Obviously nuclear bombs are artificial, but radiation as a whole isn't not man-made. It exists in the natural world. In fact, we're suffused with it. Our atmosphere protects the Earth from a lot of radiation that we would otherwise really make it impossible for us to live. So radiation suffuses the universe, and man-made radiation is in essence no different from natural radiation, although of course it may differ in the sort of quantity or the form that it takes, but its effects will be the same regardless of what the source of the radiation is. The next point, and the really big one that I wanted to address, is the confusion between irradiation and contamination by radioactive material. Now, when a substance is irradiated by radiation, that means it's been exposed to radiation. So it's been in the presence of alpha particles, beta particles, or most often gamma rays. So it's been irradiated. It's been exposed to that radiation. That means the particles have interacted with it and it's had whatever effect the radiation has had on the substance. But once you remove a substance from the source of whatever the source of radiation is, there is no lingering effect of the radiation. I mean, if the radiation has caused some damage to the substance, obviously that will linger. But it's not as if that the radiation somehow contaminates the substance so that it then becomes radioactive. And this is the key point. A substance does not become radioactive by being irradiated. It doesn't work that way. It's not like if I take a cold substance and then move it near to a hot substance, it will warm up, and then I take it away, it's still hot, and it can actually then go on to warm up other things. Radiation is not like that. If you take a normal substance in, irradiate it, yes, it will be exposed to radiation, but then you take it away again, it's still a normal, ordinary substance that just has been in the past exposed to radiation. It's been irradiated. It is not radioactive. It cannot irradiate other things. There's no ongoing effect other than whatever direct damage is caused by the initial irradiation. Some foods are irradiated, and this is a way of protecting them from the growth of bacteria and other microorganisms. And it's in no way harmful to you because it does not make the food radioactive. Now, there are some things which can make materials radioactive, and generally this happens when it's contaminated by radioactive material. This generally happens when the actual original, or part of the original source of the radiation is dispersed in some way and then comes into contact with other substances. So this happened, for example, in Chernobyl or in other nuclear accidents where radioactive material from the fuel rods that was being used in the core was well, it burnt, it exploded, it was and thereby dispersed throughout the atmosphere. It was particularized and carried by wind and rain and other forces into the surrounding area. Now, this is different because it's not that the surrounding area was all irradiated. In fact, the radiation is not going to travel that far. But what can travel are the particles, the small particles that you often can't see of uranium, which are continually going to be emitting radiation. These can contaminate people and plants and objects and really anything that comes into contact with it and continues to emit radiation. It's going to be dangerous to anything that's nearby the contaminated object. That's why radioactive substances should be well contained. Then it's only an issue of risk of irradiation. But if it's not properly contained, there's also an additional risk of contamination, which is much more dangerous because then anything that's contaminated can go and contaminate other things, leading to a spread of the root cause of the radiation. So that's the key distinction between the irradiating something and contaminating it by radioactivity. Irradiation does not cause lasting risk, whereas contamination does. So that's really all I wanted to talk about today. Hopefully you found this episode informative. If you'd like to support the show, I would appreciate some feedback on iTunes, if you can leave a review there. I've also got a Facebook page for the podcast, which you can like and share with your friends and so on. If you have any questions or suggestions or comments or anything else or ideas for future episodes, you can email me. My address is fods12@gmail.com. That's fods12@gmail.com. Thanks for listening, and I'll talk to you next time.